Hi, this is Bob Westervelt. I'm very happy today to introduce Phillips, who he's from the physics department in the University of Illinois at Urbana-Champaign. I've known him for quite some time. He's an expert in thinking about how electrons strongly couple in low-dimensional systems. PhD from the University of Washington, 1982, went on to a Miller Fellowship at UC Berkeley, then to MIT, working in the chemistry department, faculty, to the University of Illinois. He's won a number of honors on top of the Miller Fellowship at Berkeley. He became an APS Fellow in 2002, and then a Fellow of the AAAS in 2012. And so superconductivity is definitely, and strongly correlated states are definitely a hot topic in what people in the center are doing, because we have all sorts of things showing up that people don't understand theoretically. And so I really look forward to hearing his talk. Philip.
Thank you very much. This work is going to be an explanation of 3 papers, 2 of which are in Nature Physics. So one is about ready to come out, and the other one is the big summary of everything is in this PhysRev B paper right here. My collaborators are 2 students, Luke Yeo and Jen Chow, a postdoc, Edwin Huang, and then a math colleague of mine, Gabriele Lanave. So let me see if I know how to advance. Yes. Okay, so as Bob said, superconductivity is the big focus. It really needs no introduction, but let me just summarize. This problem really started in 1911, and the inkling of how one might think about superconductivity was given to us by Cooper, who studied a rather esoteric problem, just 2 interacting electrons outside a sea of non-interacting electrons, and the sea is demarcated by a Fermi surface. And what he showed is that these 2 electrons, which have this attraction between them, and this operator creates a pair of such electrons, they want to condense to form a bound state below the Fermi surface, below the chemical potential. And the problem with that is that there are no available states below the chemical potential. So what this construction really tells you is that this system is unstable, and it's telling you that there's some tendency of this system to form a condensate, and you can specify the condensate with an amplitude and a phase. Now, what really made the BCS theory succinct and complete was the realization that it's really the completion of Fermi liquid theory. So let me summarize Fermi liquid theory. The key thing about a Fermi liquid is that the electrons, is that there's a well-defined series of non-interacting levels, and there's some highest level which we demarcate by the locus of points in K-space. It's the Fermi surface. And let's just ask the question, how do you break up a Fermi liquid? So it turns out Fermi liquids are fairly resilient, and if you were to take a jackhammer to it without trying to think about how you might actually do this, so you just turn on some repulsions between the electrons. If the repulsions are short-ranged, all they do is just move the levels around. There's still a one-to-one correspondence between everything here and everything over here. And what that says then is that at the end of the day, you haven't done anything. You still have a Fermi liquid. And the way of framing that is that the repulsions are irrelevant. And the mathematical statement about irrelevance is that you can scale them with a quantity which is going to 0. So it's 1 over the system size or some level spacing, and it's going to 0 as a positive power of this. So as n gets bigger, this interaction is going to 0. The only thing which is relevant is exactly the term that Cooper introduced. Electrons on opposite sides of the Fermi surface, that leads to an instability. And so Cooper was right. And the completion of that was the BCS theory. And the key prediction of the BCS theory is an equation for the ratio of twice the gap over TC. And that's this number here, 3.5. And that's the number I want you to remember. Okay, so that completes BCS theory. It's the instability inherent in a Fermi liquid. And you can ignore all the things that you might have thought were relevant. They just don't contribute. Okay, so if we start with Fermi liquids, we know we end up with BCS theory. The question I want to ask is there anything else? If we do have something else that describes a strongly interacting system, can you work out as succinctly as Cooper did what the instability is in that system to a superconducting state? And can you delineate what the new properties of that are? It clearly has to be a quartic interacting theory. And so why would one look for this? Well, one might look for this because of the cuprates. The cuprates, we know, start off their lives as Mott insulators. And so this problem goes back to nickel oxide, in which there are lots of places for the electrons to move, but the system is still an insulator. And what Mott theorized is that perhaps it costs a certain amount of energy to put two electrons in the same box. And he called that energy U. Actually, he didn't call that energy U. Hubbard called it that, but doesn't matter who called it what. The important thing is that it's a competition between an interaction and the kinetic energy. You might wonder, if we have proven that all the interactions are irrelevant and the short range ones are, then why is this coming up? I mean, what? Okay, so the question, is this the Mottness? Yes, this is the Mottness. Okay, so, but I will be very precise about what I mean by Mottness. Okay, so yes, so just hold on, I will tell you exactly what I mean by Mottness. Okay, so what Mott said is that you form a gap in the single particle spectral function. And the key point is that you don't change the size of the Brillouin zone. So there is no symmetry breaking. Okay, and I'm going to talk more about that and the precise sense in which there is symmetry breaking in a Mott system, but it's not of the standard type. So this is a real space argument. Okay, so if one is going to complete the Cooper program for a cuprate system, here's what you have to do. You have to solve the Hubbard model. And you have to do so in 2 dimensions. And then you have to illustrate Cooper's instability. And well, you can't do that. You can't solve the Hubbard model in 2D. So what has been the progress thus far? So any problem that presents itself as an intractable model, there's going to be lots of different approaches. There have been some great numerical progress using DMFT, also quantum Monte Carlo. People have focused on order, stripes, nematicity, things of that nature. And naturally, there are lots of disputes. Okay, the dispute which leads into my talk is one between Bob Laughlin and Phil Anderson. And Bob Laughlin excoriated the field back in 1997 for using any terminology related to upper and lower Hubbard bands. He says that's just nonsense because we don't know what precisely we were talking about. And a rejoinder to that was this paper by Phil Anderson, A Critique of Two Metals. And his point was that although this paper is hugely influential, it's completely misguided. And he says it's a tragedy of Mott that although He most certainly won the Nobel Prize for the Mott insulator. Slater, who couldn't think clearly about finite temperature, won the publicity battle. So what does he mean by that? And what is Laughlin's beef? So Laughlin's beef is that if you have a half-fill band, it's very easy to think about how that might insulate. All you do is break a symmetry. You break the translational invariance here. You go to something which has 2 atoms per unit cell. And since now you have half the number of k-states, there have to be 2 bands. And this band, rather than being half-filled as the original band was, is now completely full. So you've gotten rid of the Mott problem. There's no worry about why it is a half-filled band, and a band with empty states is insulating, because now the lowest band is completely filled. So the question arises, does attributing Mott insulation to a symmetry broken state of this kind leave anything out? So it makes sense to ask the question, what's the difference between what Laughlin proposes and what Anderson has in mind? And that difference is what I call Mottness. So Mottness is the explanatory residue which is left over if you attribute Mott insulation to ordering. Okay, and it turns out you can quantify this. There is a certain thing which is equal to 0, and it's the determinant of the real part of the green function at omega equals 0. There's also constraint on the imaginary part to make them purely non-trivial, but let's just say this is the quantity. And in the case of Laughlin, this is not equal to 0, but in this case, it's equal to 0. So the non-trivial physics that Mott was talking about reduces to this quantity. So let me introduce this quantity, and then use that to try to understand how you might come up with a simple way of understanding Mott physics. I don't quite understand this question. The question is, as far as order in multiple dimensions, would it be a Fibonacci? Not necessarily. The order people have been talking about is entirely one in which a translational symmetry is broken. Now, granted, that is also broken in a Fibonacci sequence, but no one has proposed that as what's going on in the Mott problem. Okay, so let's just look at a simple exercise. Let's count particles. So the simple way of doing that is just to put numbers by them. This is rather tedious. So is there a simpler way of counting particles? Yes, there is. Okay, if we wanted to count particles, one can do so by using this quantity. Let epsilon p be the energy of a particle. So whenever E, this probe energy, encounters this function, so this is epsilon p, this is E. On either side of this function is negative and goes to negative infinity for E less than epsilon p, and it blows up for E bigger than epsilon p. And so what you could do then is you could simply count the number of times this function changed sign and look at that locus of points, and that would be telling you the number of particle-like states in the system. So my definition of a particle state is something that has a pole in this quantity. So all you're doing is counting poles. So the simple way of thinking about, or the mathematical reduction of that, is the number of particles. Each momentum state can have 2 electrons, up or down, since it's non-interacting. Theta is a function which is positive, which is non-zero if this argument is bigger than 0. So all you're doing is counting the number of sign changes. So this works perfectly for counting particles if the function looks like this. However, written in this form, you don't really care what the mechanism is that makes the function become positive. All you care about is that it was negative and then it's positive, which means this function could have easily just gone through 0. And a zero crossing is very different than a pole, because zero crossing, this function can't go through zero. But this expression for the number of electrons or number of particles in the system makes no distinction between this situation and this situation. And it's this situation that actually distinguishes the Mott problem from a symmetry breaking type kind of problem. Okay, so let me tell you more about what this, what this means. Okay, so how is it that you can get, zeros? Now let's assume that the spectral function looks the way Mott said it did, that just by changing the interactions, you generate a gap and you have spectral weight at low and high energies. So as the imaginary part of the green function looks like this. Now we can construct the real part. All we do is Kramers-Kronig transform this with 1 over omega, and then you have this thing at omega equals 0. Now the numerator is entirely positive. The denominator is the thing that's changing sign. So which means there can be a contribution below and above the gap, and the stuff below will be negative, the stuff above will be positive, and hence this and this can cancel one another and give rise to a zero. So zeros have to do with the balancing of the spectral weight at high and low energies with this moment. Okay? So the clear statement is that the determinant, because you want these to be within the same band, not in different bands, as in the case with Laughlin has been talking about, so you want this determinant of the real part of the green function to equal 0. Okay, and this only happens in strongly correlated systems, this precise mechanism for generating zeros, because you also want the imaginary part to equal 0. Okay, so zeros have to do with, there's no propagation, of course, you have a breakdown of the particle concept. A simple green function with a pole can never give rise to zeros. And this is what I termed Mottness. Okay, because you can't separate the high energy and the low energies. They're completely inextricable or inseparable, because removing an electron changes the spectral function both at high and low energies. Okay, and one of the questions that comes about is, does the particle density really equal the number of zeros plus the number of poles? Okay, so what is the minimal model for Mottness? Okay, now what I want to tell you is that it's not the Hubbard model. You don't need anything that complicated. Okay, so let's look at a Fermi liquid. In a Fermi liquid, everything is doubly occupied below the chemical potential. The system's non-interacting. And a key feature of Fermi liquids is that their particle addition, this part above the chemical potential, and the removal spectrum are completely equal. Removing and adding a particle, it's the same thing. Okay? So this is this particle-hole symmetry, which is an intrinsic property of a Fermi liquid. Okay, in a non-Fermi liquid, what would be the simplest way of generating that? Well, the simplest way of generating that would be if somehow you could have single occupancy below the chemical potential. Okay, the reason why these are doubly occupied is that there's no interaction. So what you would want is single occupancy below the chemical potential, and you want that from a non-trivial model that keeps time reversal symmetry intact. Okay, now another thing about non-Fermi liquids, in particular the cuprates, is that there's a difference between the spectrum having to do with adding a particle and removing a particle. It's fundamentally asymmetric. And you can see that by just flipping this around, and this doesn't look the same as this. Now, this bothered Phil Anderson tremendously, And he says, I remain baffled by the almost universal refusal of theorists to confront this evident fact of whole particle asymmetry head on. So he viewed this as an intrinsic feature of strongly correlated systems and was bothered by the fact that no one was really taking it seriously. In other words, it wasn't the starting point for developing a theory. And this, you just look at any number of data, and you see this asymmetry between the addition and removal parts of the spectrum. Okay, so if we take this seriously, let's ask a simple question. If putting single occupancy below the chemical potential is key to getting a non-Fermi liquid, does that also generate particle-hole asymmetry? Are these two things sort of related? Okay, so to do that, let's take a closer look at a Fermi liquid. So a Fermi liquid, as we know, we just need to look at the kinetic energy, and this is just the occupancy for either spin state. And there's some dot here, but it's just the stuff that's irrelevant. I'm just going to go through this paper by Anderson and Haldane, and no one seems to know this paper, although for me, this paper has been absolutely crucial. This paper's gotten 3 citations. Okay, here's the key point. Their key point is that, written in this way, it's clear Fermi liquids have 2 conserved currents, one for spin up and the other for spin down. And there are 4 objects which make up these currents: the annihilation operators and the creation operators, which means the actual symmetry group for a Fermi liquid is O4. Now, O4 has 2 subgroups which are relevant here. And you can divide them into things which are proper rotations. These proper rotations have a determinant of 1, and the subgroup here is SO4, which is just 2 copies of SU2, essentially. And what's left over are the improper rotations. And the improper rotations have a determinant of -1. I'll tell you exactly what those are, but you can just get that by taking the quotient of O4 with SO4, and that leaves a Z2. The Z2 is in momentum space, not in real space. And I'll tell you exactly what that is. Well, we can think about this Z2 in the following way. If you just look at parallel transport on a Mobius strip, one traverse gives you a sign change. It takes 2 to come back to the original position. Okay, so how does that play out for a Fermi surface? Here's how it plays out for a Fermi surface. At the Fermi surface, EP is equal to epsilon F, which means the Hamiltonian is equal to 0. If the Hamiltonian is equal to 0 at the Fermi surface, then one can, with impunity, make the following change. You can send NP up to 1 minus NP up, keeping the down sector the same, and you haven't changed anything. So in other words, you can undergo, at the Fermi surface, this particle-hole transformation. That's why they're particle-hole symmetric. This is the Z2, this is the extra Z2 symmetry that Haldane and Anderson noticed. Okay? So, if you want to destroy a Fermi liquid, what you have to do is destroy this Z2 symmetry, this hidden particle-hole transformation, and we know it's present in all Fermi liquids. All you have to do is come up with an interaction that destroys this. Well, what's the simplest interaction that destroys this Z2 symmetry? Well, it's just this interaction. Because if I were to make a particle-hole transformation here of just one of this species, not both of them, I would change the sign of this interaction. You generate some other stuff, but you don't care about that. It doesn't have to do with the interaction. This interaction would change sign. And that would violate the particle-hole symmetry. Okay? So this is a simple enough, this is a simple enough interaction that breaks this particle-hole symmetry that Haldane and Anderson that at least said was present in a Fermi liquid. And this is the thing that I've shown you experimentally is relevant for looking at the cuprates. Now, why would this break Fermi liquid theory? If you simply looked at the scaling dimension of this relative to the Fermi surface, you would find this has scaling dimension -2. Okay. Yeah, this is scaling dimension -2. And which means it's relevant. It's not scaling to 0, which means once you put this term in, you no longer have a Fermi liquid. This is a relevant interaction. And this exercise will tell you then that there has to be a new fixed point. You no longer have a Fermi liquid theory, you have something else. And precisely what that is, I will tell you. But this is the form of the Hatsugai-Kamoto model. Now note, this is essentially the Hubbard model, but in momentum space, which means you can derive this, but you have to include something in real space that's completely non-local. Okay, now what complications that introduces, or how does that allow us to think about the original problem? That's what this talk is really about. Okay, so the general HK model is one which has the kinetic energy in this interaction. And this is, notice these two terms commute. And you would have thought there would be no interesting physics coming out of this if these two terms commute. But that is not the case. This is a solvable model. And it exhibits a Mott transition. Okay? And it's solvable because I can write down the single particle green function exactly. And here it is. There's some weight here that now depends on the occupancy, unlike a Fermi liquid. And it's a sum of two poles, which means you've broken the simple pole of a Fermi liquid into two pieces. And those are the upper and lower Hubbard bands. So the precise prescription for Hubbard band terminology, which is what Laughlin was looking for, is given right here in this model. It's not the only way of getting this, but it is at least a precise way of knowing what we're talking about when we use such terminology. And because this is the sum of two poles, you can never write it like this. Okay, so there's a Mott transition, which means we have two bands, and here they are. This is the upper one, this is the lower one. And this surface between them, since I have stuff at high energy and low energies, and I'm equidistant from each of them, by looking at this surface, this is the surface of zeros. Okay, so anytime this one lies above the chemical potential, you have to have zeros. Okay, and the things in the lower band, I'm going to describe by this operator because it really depends on not having another electron in these states. And in the upper state, this depends on an electron already being here, and hence these bands are not described by fundamental excitations like an electron. They are composite excitations. Now, if I were to decrease U, the upper band would cross the chemical potential, and hence double occupancy would now be possible in the ground state of the system. And I have some symbols here. Omega 0 represents the empty part of the spectrum. This is the half-filled, the singly occupied part of the spectrum, and this is the doubly occupied part of the spectrum. So I'm only counting this per spin, which is why these are 1.5 and 0. Okay, so already we have exactly what we need. Below the chemical potential, we have a singly occupied part, and that was not possible in a Fermi liquid. But it's not singly occupied in an elemental sense, it's in a composite sense. Okay, so let's look at the Mott transition. Now, it's fairly complicated because I've told you already there are two ingredients here. I have double occupancy here in the metallic state. I have no double occupancy here and a surface of zeros. So let's look at these separately. Here is the indication of the Mott transition in what's called the HK model. It's where the double occupancy goes to 0 and the bands separate. And this happens at a well-defined value. Now, if you were looking at this transition in the Hubbard model, you would have to calculate this in real space. And you'd see that this goes to 0, or at least it certain, depending on how you calculate it. If you use a more complicated computational technique, well, it drops, but then it sort of trails off. It never quite goes to 0. The only difference between this and this is in momentum space, this is in real space. So the metric of the Mott transition here and here is just slightly different, but it's telling you the same sort of thing. Now, the fact that this never goes to 0 is actually important. That is the key difference between the Hubbard model and the HK model. One, this is tractable, this is not tractable. The reason why this doesn't go to 0 is that every correlation function that you write down in the Hubbard model has T over U corrections. And by that I mean the following. Let's look and see what the HK model leaves out. If I have an empty site in the Hubbard model, that is not a conserved quantity. I can have mixing with the high energy sector or the low energy sector. If I just let this run, I don't end up with just one empty site. I can end up with any number of them. In this case, because of how I ran this, I think I end up with 2 empty sites. And the cost of that is you are mixing with the doubly occupied sector. That physics is inherently mixed with the Mott gap in the Hubbard model. The HK model separates these two things out. It shows that you can come up with a non-trivial, strongly correlated gap without this dynamics. And this dynamics is called dynamical spectral wave transfer. And it's coming because the kinetic part and the interaction the interaction part do not commute. Okay, so that part is absent. And if that's what you're interested in, you shouldn't look at the HK model. But that's just a small T over U correction. Okay? Now, the thing which is present in the HK model is just static spectral weight transfer. The moment you dope the system, spectral weight which was up here is transferred down. And if it's transferred down, this means that this line of zeros is no longer going to be symmetric around the chemical potential. If it's not symmetric around the chemical potential, that has a profound consequence. So if I were to calculate the particle density by just eyeballing it and counting out the part that is empty, which has 0, the part which is singly occupied, that's this right here, and the part that's doubly occupied, it should be this total area underneath here. Okay? I could also do it the way Luttinger tells me. I look at the sign changes. Well, there's the sign change here, 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 and here. And I asked the question, do these sign changes add up to this area underneath here? And the answer is no, because this does not equal that. So the moment you have zeros, you're going to see that you violate the Luttinger count. And this is something that lots of people have worked on at both Harvard and MIT. And I just want to say that this is still an unresolved problem, how you get around not satisfying the Luttinger count, but it seems to be a generic feature of Mott physics that you do violate it. And it's not just in this model. If you look at the Hubbard model, you have a surface of zeros. And this is the state-of-the-art simulation. You have a surface of zeros. And what this gives rise to is, look at the stars and compare them with the non-interacting band. You get a violation of the Luttinger count. Okay? So these two features, a gap and then a violation of the Luttinger count, and that's indicated by deviation from this purple region here. Those are generic features of Mott physics, not just of this ultra-solvable model. Okay, so let's go back to our original question. And ultimately, this is tied in with Bob Laughlin's question. How do you destroy a Fermi liquid and understand Mott physics in ways that you can really put your fingers on? Well, you don't need to do something as blind as taking a jackhammer. Let's replace that with just this interaction. This is a relevant interaction. And what it does is that it splits the spectrum into two pieces, one at low and high energies, and there's a gap, there's a Mott gap between them. And we can calculate everything about the system. So the moment you have this interaction, you flow away from a Fermi liquid. And this interaction does exactly what Anderson wants. It generates particle-hole asymmetry because it breaks the underlying Z2 symmetry of a Fermi liquid. Now, one might ask the question, how is this related to the Hubbard model? Because this is not exactly the Hubbard model. Okay, so one might ask, if you have the Hubbard model down here, how do you get up here? Well, if you just Fourier transform the Hubbard model, this interaction, you'll see that there is a part that looks like this, but it's coming in with a very small coefficient that's vanishing in the thermodynamic limit. But this interaction is also relevant, and it's scaling 1 over s, but s is also scaling 1 over n, and hence this is going as 1 over s, and hence it's producing something which is also relevant. So my point is that both Hubbard and HK are related because they have a part which is relevant to both of them. So I think what this is telling you is that they lie in the same universality class, and that's why they both have gaps. They have these surfaces of zeros, and there's a more exotic sort of treatment of this problem. But I want to get on to superconductivity, so let me finish this Mott part right now and go on to superconductivity. Okay, so we have a control model. We know to go and do all the calculations. And let's now just summarize this. So in the evolution of thinking about, no correlations to a Fermi surface, you have a Fermi liquid, you have a Fermi surface, you think about excitations across it, and this gives rise to a BCS superconductor. The terminus of this evolution, I think, is Mottness, and you no longer have the simple sort of levels in terms of occupancy that you did in a Fermi liquid. You have singly occupied states below the chemical potential. And it's this singly occupied sector that's going to introduce all the non-trivial physics that deviates from BCS. Okay, so now let's ask the question, what happens with superconductivity? So we can do the same thing Cooper did. With this model, we can introduce pairing of states above the chemical potential, the empty part, and we can ask the question, is there a pairing instability? And the pairing instability will be indicated by this quantity being negative. Okay, so you can go and do that calculation exactly, and in fact, you can see that yes, this quantity is in fact negative. So this was in the first Nature Physics paper, and this formed the basis for the first indication of an exact calculation of the Cooper instability in a doped Mott insulator. Okay. Now, since this model is ultra solvable, you can go and calculate the susceptibility exactly. And here's the susceptibility. It's diverging right here. Here's its form. Chi0 is just the susceptibility in the HK model. As in a Fermi liquid, it is also growing. And because this is growing, the denominator can actually cross 1. And when it does, you end up with the divergence. And let's say this determines TC. So we know from the exact calculation, the ground state is a superconductor if you introduce a pair interaction. So I don't care at this point what's causing that. What I care about is carrying out the Cooper type analysis for a doped Mott insulator. Okay, now what made BCS is that they introduced a wave function. And from that, they were able to calculate all of the properties of the superconductor. Now, this wave function didn't just describe the superconducting state; it also describes the normal state. And because you only have two occupancies, things are either empty or completely full. You only have two parameters here. In our case, because we have singly occupied stuff below the chemical potential, which does introduce some problems having to do with entropy. I haven't talked about that, but full disclosure, yes, there is a problem. But once again, it's the universality class that saves you. In this case, we have three possible occupancies, which means our wave function has to have three variational parameters. They have to do with the empty part, the doubly occupied part, and the singly occupied part. Okay? And one can do this, and the calculation, BCS taught us how to do these calculations. They can be generalized. And the key thing that you introduce when you have the wave function is the gap, and you can look at the ratio of the resultant gap to TC, and since you have different exponents here, this ratio is actually going off to infinity. So this is non-BCS superconductivity. This is the first indication that something is really different when superconductivity evolves out of a doped Mott insulator. Okay. Now, we can put away the wave function for the moment and just work with the free energy, which we can calculate. And here's what we found. We know all the states. We can actually go and do this calculation. So I have four different things here. Here's the free energy at a temperature that's sufficiently high that nothing interesting is going on, and it's featureless. So this is T bigger than a temperature I call the temperature at which you first get a non-zero solution for the gap. That happens here. Note, this is degenerate with this, which means the transition to the gapped state, the superconducting state, seems to be coincident with the solution at zero, with the free energy having two degenerate minima, one with no gap and one with a gap. And because these are degenerate, it seems as if the transition really is now first order. Okay? So, and then as you lower the temperature even further, that's this one. And the one in which this goes away and you only have this complete unique minimum, that temperature is actually equal to the TC at the temperature at which the pair susceptibility diverges. Now, the problem with that analysis then is that it was assumed that the pair susceptibility was relative to the normal state. But what this is telling us is that there's actually an instability before then. So we have to rethink that and really view the transition as a first order one. And we have no indication that mean field theory is not really working here. So it seems as if the transition really is a first order transition. And that's one thing that's fundamentally different starting from a doped Mott insulator. Okay, and that I'm sure has lots of experimental consequences, but it might be very subtle. Okay, so as you can see, this thing is not unique. Okay, so BCS would give you this curve. What we're getting is this. Now, there's still a jump in the heat capacity because anytime you add to a Hamiltonian something that has a temperature dependence, there's going to be a discontinuity as you lower the temperature. And you can confirm that right here, this heat capacity over that in the normal state. And so here's the jump. And it's getting bigger as you increase U. Okay? So there is still the heat capacity jump as one expects. Okay, now other things that one can calculate: the condensation energy. When the system superconducts, the energy is lowered, and in BCS, this quantity is equal to -1. In coming out of a doped Mott insulator, it's much bigger than that. I can go all the way down to -2. Okay, depending on the ratio of U over W. Okay. Okay, now, what about the excited states in the system? Okay, one defines these operators which define the excited states by acting on the BCS wave function and annihilating it. And one can do this, and one sees that the excitations in BCS are superpositions of particles and holes. There's some linear combination you're supposed to take here, but sigma is just a spin. Now, in a doped Mott insulator, the elementary excitations are not particles and holes. They're these composite objects, which means this is the wrong starting point. These are not the elementary excitations of a superconductor that comes out of a doped a Mott system, which has strong correlations. The new excitations we call pions. This came out of our first paper, and these are just the order of our initials. And here's what these things are. There's one for the lower band, and there's one for the upper band. So these operators create the composite excitations that define the upper band, and these define the lower band. Okay. So in a BCS superconductor, this is what you have. You just have a gap that opens, and this is equal to that. The weight here is equal to that. There's some backbending, but it's just the same thing. That's not the case here, because you've broken particle hole symmetry, and the weight here is not equal to the weight here. And note, even the upper band has spectral weight, and there's a gap that forms up there. Now, the reason why that is crucial to cuprate phenomenology is that people have noticed that even at high energies, there's something going on when the cuprates superconduct. Okay, so these are the pion bands, similar to the Bogolubov bands in a BCS superconductor. Okay, so what I'm alluding to is this spectral weight transfer. Okay, so what they did experimentally is they defined the low energy part as just a sum rule. If you just integrate the conductivity up to omega, which is 1 EV, and this is really tied to a sum rule that Tinkham actually developed, and this should define the low energy part of the spectrum, and the high energy part of the spectrum here up to the end of the upper Hubbard band. Okay, and what they found is that these two things talk to one another when the system becomes superconducting. And here it is. This is the low energy. This is the high energy part. It's going down, as it should. But there's a kink here, and that's picked up by an increased spectral weight here. So the rule for determining this is looking at the optical conductivity. And what they notice is that although this is this change in this relative to what this was before it superconducted, this region right here, it's just a 3% increase. Now, this is a small thing, but they noted that although this is small, it's sufficiently large to account for the condensation energy, the lowering of the energy when the system becomes superconducting. Okay, now this is mixing between stuff at 2 EV and stuff at 0, below 1 EV. Okay, now you think if anything is a low energy property, it's the superfluid density. But we've known that that's not been the case for a very long time in the cuprates, and this sort of really lays plain that that is really the case. Okay, now we can't really get the conductivity. So what we decided to look at is there a transfer of spectral weight between the upper band and the lower band when you go through the superconducting transition at TP? Okay, so what we're looking at is the weight as a function of as a function of this coupling parameter, the superconducting coupling parameter, relative to the weight when this quantity is equal to 0. In other words, the superconducting weight over the weight when the system is in its normal state. And what you find is this thing does start out at 1, so it's good. This is bigger than 1. Okay, so there's increased weight in the lower part of the sector. And this is decreasing as you increase U. And this decrease, although this is just a one particle probe, it's not the actual conductivity. This is actually increasing. And this, this increase relative to the weight in the normal state is roughly what you see experimentally in the two particle probe. Okay, so one would have to go and calculate the conductivity. That's a much more involved thing, but this is giving us some indication that there is this mixing between the upper and lower bands, as there should be, because the basic excitations don't just live in the lower band. Okay, and it's coming about because once you introduce pairing, you no longer have the you no longer have the commutativity that the HK model had, and which means you have dynamical spectral wave transfer, and that mixes everything up in the doubly and the singly occupied sectors, and hence you're going to see some aspect of transfer between the upper and lower bands. So we think this is a general effect that's coming from Mott physics. Okay, now one of the last things I want to show you is, since I'm at Illinois, of course, the Hebe-Slichter peak is a very prominent thing. It's the thing that led to BCS, really becoming on the map. As you crank, we can calculate this the spin lattice relaxation time. At U equals 0, you can see this is just BCS theory. There's an enhancement of the spin lattice relaxation rate below TC, and that's because everything's acting coherently. This is gone as a result of Mottness as you crank up U. And this is seen experimentally in the Coupe rates, and it's been attributed to spin, spin fluctuations. None of that is here. We just have a bifurcation of the spectral weight by Mottness, and that is sufficient to give rise to a suppression of the Hebe-Slichter peak. I could go on and give you more properties, but I thought I would just tabulate how different superconductivity is from BCS. So here's BCS. Here are all the experimental observables, susceptibility, the gap. The gap seems to turn on at a temperature distinct from where the susceptibility diverges. This ratio is now not that. We have fundamentally new elementary excitations in the superconducting state. There's no Hebe-Slichter peak, and the condensation energy changes fundamentally. We can also calculate this. Essentially, everything BCS can calculate, we can also calculate, and we have in this longer paper, because we have the machinery to do that, but now it's coming out of a doped Mott insulator. Okay, so to summarize, by focusing on the fundamental symmetry that a Fermi liquid that you have to break to destroy Fermi liquid, you can get fairly far in coming up with a simple tractable model that has a feature that is shared also by the more fundamental model, the Hubbard model. And my claim is that all of this is in the same universality class. Just like Fermi liquids, all you need is p squared over 2m, and you're done. I think all you need here is just to go and break the symmetry, and everything else you add, you're adding in more complications like magnetism, et cetera, which solves all the entropy problems, but it isn't changing anything fundamental about the physics. And so in terms of computational power for a doped Mott insulator, I think this is as good as it gets. So that's all I have to say.
Oh, well, thank you very much. That's interesting. I mean, I think that's what people are trying to figure out as you have correlated Mott systems and also superconductors, and how does this go? For questions, people should type the question into the chat part of Zoom on the bottom, and then I could read them. I guess I have one to start out up with, and then for the experimenters, what would be the right things to do to identify?
Okay, so right. I guess one of the big questions is the transition really second order? Just because there's a jump in the heat capacity does not mean that it's second order, as I've pointed out. So a basic thermodynamic measurement to see if there's a latent heat would be one thing that I would suggest. The other thing is the fact that there's spectral wave transfer between the upper and the lower bands plays fundamentally into where the superfluid density is coming from. Now, we're in conversation with Seamus Davis about QPI type scattering in the superconducting state that is a result of the upper Hubbard band. And we are trying to see what are the experimental signatures of that. We have predictions. So far, he hasn't seen any effects of the upper Hubbard band, which is very strange because it's there. Certainly the superconducting state in the cuprates tells us that it's there because you're seeing this transfer. So I think now that we have some computational handle in a controlled way, one can ask the question, can the experiments be tailored to now probe that?
Yeah. Okay, thanks. We have a question from Gabrielle Schlater. What would be a good rule of thumb to know when to employ which model? Hubbard versus this, et cetera, question mark.
Right. If you're interested in magnetism, you should use the Hubbard model. If you're interested in the generic features of Mott physics, the gap, the static spectral wave transfer between them, and I would argue even the properties of superconductivity, then all you need is the HK model. There's something else I was going to say. Yeah, I mean, I would say what one would like to do is, but you can't do this, so I'm not even sure it's worth pointing out, is derive a theory of superconductivity from the Hubbard model and then sort of match that onto this. You can't do that. But one thing we are trying to do is slowly introduce all of the other things which are present in Hubbard, the stuff that gives you magnetism that are warm or long range stuff, and then show that that doesn't affect any of the conclusions that we have reached. And that is a way of sort of shoring up the gap between HK and Hubbard.
Okay, great. Let's see. Other questions? Please type into chat.
Yeah, there's another question here.
Okay, go ahead and read
Very
it.
interesting. Thank you. Okay.
Go. Vigo, which is the most suitable model to apply for superconductivity with operating temperature at liquid nitrogen level?
Okay, so liquid nitrogen. So you're talking about the cuprates, right? I would say either one. As I said, it depends which thing you're trying to model. If the system really is a doped Mott insulator, then I would say just go and use the HK model. It has a Mott transition. You can go and do all the calculations. There's no reason. I mean, Hubbard is intractable. So unless you want to really frustrate yourself, go ahead and use Hubbard.
Okay. One last question. Okay, if not, thanks very much for interesting talk, and thanks again.
Okay. Thank you so much.
Bye, thank you.
Okay. Bye-bye.
Bye-bye.